For the next example, which is the same region of rotation, so what are we going to have? It's important to first plot graph. And what do we have? The diagonal line y equals to 2x and the parabola y equals x squared. Alright? However, notice in this case we are not rotating about the x-axis or the y-axis. Instead, we are rotating this region about the line y equals to 4. In the previous example, we did the rotation about the line y equals to -3. It was a line below the region of integration, below the just below the region that we rotate. But in this case, the line y equals to 4, it's going to lie above the region of rotation. Since 1 and 2, we found that this value of y is 2 by finding the points of intersection. So our region of rotation will be this, alright? Or axis of rotation rather. So this will generate the following solid. Whoops. We need more space in here. So if we think of this axis of revolution as a mirror, well, how many units away is our region of rotation from the axis of revolution? Isn't that 1 and 2 units? So when we rotate this region, so we're gonna go 1, 2, 3, 4. So that's going to look like this. All right. And of course, you can imagine this region being rotated, hollow in the middle. Right. So we have a washer in this case, not a disc. But the approach, it's very well the same as if we were finding the disc. But the difference is going to be in the next section when we set it up in terms of the shell method otherwise. All right, so let's see. So in this case we want this volume right here. However, in the previous example, notice how we had the region of integration above the axis of rotation, but this time we have the axis of rotation at the top and the region of rotation, the region that we rotate, at the bottom. So everything will go from the axis of rotation to the region. But notice, from the axis of rotation, we are going to have again an outermost radius and an innermost radius. The outermost radius will be, in this case, the parabola, because that's where the points in the outermost region are, and the innermost will be the line. So we're going to have a similar approach in here. So let's see. So this time we want the following. We want this, and this is going to be equal to the whole solid, and in this case the whole solid, it's going to be this minus, in this case we want to subtract this hollow part in the same way that we did last time. Yes, question?
The two lines intersect at 4 equals y.
4 equals y. Well, so no, the intercept right here is 0 and 2. Oh yes, that's gonna be that's true. Oh yes, so ultimately, well, you know what, let me change the number. How about, okay, instead of, let me do y equals to 6. Otherwise it's going to be it's not going to be this, it's actually not going to be a washer, but it's going to be a this. Thank you for pointing that out. I should have changed that. Okay, so it's going to be the outermost radius minus this hollow part, and that hollow part is going to be this one right here, all right? Well, so big R, which and little r. So the top in this case, the individual top, the individual top minus bottom for the smaller region. So in this case, this is the line y equals to 6 for both, and in this case the bottom part is y equals to x squared and y equals to 2x. So again, in the same way that we did last time, top minus bottom, so that's for big R, that's 6 minus x squared, and little r is 6 minus 2x. Alright, and well, to find the volume, to set up the integral for the volume, that's going to be pi times the integral from a to b, outer radius squared minus inner radius squared with respect x. And well, we have expressions for big R and for little r respectively. But again, we're just setting up this integral. We're not evaluating this integral. That's going to be a typical, exam question in which you're going to be given this, in a way, complex situation. It's going to give rise to an integral that will take a good minute to compute. Because of that, you will just being asked to set up the problem only. So that's going to be 6 minus x squared, quantity squared, minus 6 minus 2x quantity squared with respect to x. Oh, the limits of integration from 0 to 2, by the way, because these are the same points of intersection from the previous problem. And well, if you want to find this volume, you should get as a final answer 32 pi over 5. All right. Yes.
Can you explain why they changed the y equals 6 again?
The y equals x. Oh, the y equals to 6?
Yeah.
Yes, because the point of intersection here is x equals 0 and x equals 2. But when we evaluate x equals 2 to any of the functions, the value of y equals to 4, and I would have gotten the axis of rotation exactly intersecting the region, so we wouldn't have a hollow part, so we can illustrate this idea instead. So that's why I changed it. All right. Okay, let's look at the, yes.
How do you determine y equals x squared and big R?
Y equals x squared, well, because from the axis of rotation to the outermost, the outer radius is bounded by the curve right here, which is x squared, and the inner radius, little r, is bounded by the diagonal line y equals to 2x. All right. So same region for example number 6. So how about we just plot it? First of all, let's plot it. Y equals to 2x, and the diagonal and the curve, the parabola. All right. So from here, in this case, they're asking us to find or to set up the integral that finds the volume, while to rotate this region, in this case about the line x equals to -5. So this one is not going to be a horizontal axis of revolution, but rather a vertical one. So I'm going to go to -5. So that's -1, 2, 3, 4, 5, 6, 7, 8, 10. Right. Okay, so that's our axis of rotation. X equals to -5. All right. So when we rotate this region, we should obtain a solid reflected this way. Alright? And it's going to rotate this way. Alright? With this hollow region in the middle. Okay? Well, in this case, because we have an axis of revolution that is vertical this time, in this case we need functions of y, not functions of x like we did in the other rotations, in the other examples. Well, so we can very well solve the two equations for x to get functions of y in each case. Y equals x squared is the same as saying x equals plus or minus the square root of y. But in this case, we can just take the positive part, because notice this parabola right here, which is in the first quadrant, it's going to describe positive roots in this case. So we can actually just erase that plus or minus and leave it as simply square root of y. And then y equals to 2x, we can solve for x, 1/2 y. All right? Okay, so here is where we need to set up the volume calculation. Well, so we're rotating about this vertical line, x equals to -5. From here again, we have an outer radius and an inner radius, right? An outer bound and an inner bound for the region. The outer bound will be, well, the parabola, however, not in terms of x, but rather in terms of y. And the inner radius will be the diagonal line, not 2x in this case, or half of y, which is in terms of y. Well, this time we're going to set the integral the following way. So this is the axis of rotation, and we want this solid this will be the whole volume minus the hollow part. All right, are you guys following me with this picture on how to set up the integral, or rather how to visualize what we want to obtain? Well, in this case, we're going to do not the top minus bottom like we did with functions of x, but in this case, what do we do when we deal with functions of y instead? If it's not top minus bottom, rightmost minus leftmost, all right? So our representative rectangle to visualize that will be a horizontal, all right? And well, so that's a big R, little r, and well, this is the vertical line, x equals to -5, and this is x, no, not x, yes, that's x, and then x equals to root of y. While over here, this is the line, x equals to -5, and this is y, or rather x, equals to 1/2 y. All right? So in this case, we set up the integral using functions of y, where big R will be rightmost minus leftmost for the first region, and rightmost minus leftmost for the second region. So that's going to be the square root of y minus -5, and little r, that's 1/2 y minus -5. But subtracting -5, isn't that the same as adding 5? So big R, that's the square root of y plus 5. Be careful, this plus 5 is not going to be inside of the radical, it's outside. And 1/2 y plus 5. So we have everything we need. We have the big R, we have the little r. We may go about setting up the integral. So let's see. Volume, which is pi, integral not from a to b in this case, but rather from c to d, big R squared minus little r squared with respect to y this time. So that's going to be volume equals pi. Well, how do we get the limits of integration? Because, well, we already got the limits of integration from the previous couple problems to be x equals to 0 and x equals to 2. But we want the limits, the corresponding order pairs, for, because in this case we need the limits in terms of y. So what's the value of y when x equals to 0? Well, it's 0. And what's the value of y when x equals to 2? And you can plug in the number x equals to either equation, because those points of intersection came from sending these two equations. Isn't that y equals to 4? So the integral is going to go from 0 to 4. Rather rightmost, or big R, root of y plus 5 squared minus 1/2 y plus 5 squared with respect to y. Okay? So this would be the integral to compute that volume. And of course, we're not going to compute the integrals, otherwise that'll take us at least half a lecture having to square the binomials, radicals, and the like. All right. However, I have the result just in case you're curious, in case you want to evaluate them on your own. 40 pi over 3. Okay. Wait a minute. No, that's not the result. That's 16 pi. No, that's the other one. 16 pi. Yes. Can you repeat again?
So on the exam, would you expect to evaluate it?
No, so for shorter integrals, you might be asked to evaluate the integral, but like regions that are a little more complex, like this one, you will just be asked to set up the integral. So mostly you will be tested on the concept of either top minus bottom, rightmost minus leftmost, and how to set up whether the dishwasher method or the next ones, which are cross sections or shell method.
Could you repeat what that line in the sheet is? It's the next to bar and little r.
This?
That's the last one.
Right here?
In between those.
This? Oh, this one right here. Oh, so that's the volume we want. So this is the region right here. The 2x and the y squared, but this is the axis of rotation which lies to the left of the region. On the last example on this topic, we're going to have a situation in which this vertical axis is not on the left but rather on the right. So let's have a look at this one. So set up the integral that finds the volume of a solid obtained by rotating the region bounded by, okay, same, y equals to 2x and y equals x squared. But in this case, our axis of rotation is no longer to the left of the region of rotation, but rather it's to the right, where the line x equals to 6. So this is 1, this is 2, 3, 4, 5, 6. So we can draw this dashed line right here that represents the axis of rotation. And I'm going to go 1, 2, 3, 4, 5, 6. And draw this. So that's the solid that we are going to obtain this time when rotating about the line x equals to 6. So in this case we want to refer to this region right here. Okay, so see how the axis of rotation this time is to the right, as opposed to the previous example, we have the axis of rotation to the left. All right, I mean that the logic will be the same, rightmost minus leftmost. Just make sure to have the correct position of the region of rotation and the axis of revolution. So in this case, we want, in the previous example we did this, all right, because we had the axis of revolution to the left, but this time we're going to do this. The axis of revolution will be to the right, and we are going to find this volume by finding the whole volume, and the whole volume would be all this. And we are going to subtract the hollow part, and the hollow part is bounded by the curve in this case. All right, again, from the axis of rotation, we have an outermost radius, and that our outermost radius is bounded by the diagonal line y equals to 2x, or x equals 1/2 y, and the inner radius is bounded by the graph of y equals to x squared, or x equals the square root of 5. All right, so let's label again: big R, little r, and what do we have here? This is x equals to 1/2 y, and this is x equals to 6. Then this is x equals to root of y, and this is also x equals to 6. And individually again, we will do rightmost minus leftmost, rightmost minus leftmost, so big R will be rightmost, which is 6 this time, minus 1/2 y, and little r, which is 6 minus the square root of y. And we have all the information that we need to set up the integral. So again, volume equals pi times the integral from c to d, and that's big R squared minus little r squared, with respect, in this case, with respect to y, not with respect to x. Oops. And well, again, identify the points of intersection 0, 0 and 2, 4. In this case, the limits of integration c to d are in terms of y. That's going to go from 0 to 4. And well, that's big R squared, 6 minus 1/2 y squared, minus little r, which is 6 minus the square root of y quantity squared, with respect to y. And that's the integral that will find the volume for us of this region being rotated about the axis x equals to 6. And if you want, in case you want to evaluate the integral on your own, I have the result, 40 pi over 3. Right. So, well, my advice is so you can look at all these different examples that we covered, whether on your notes or go back into the videos once I put it on Canvas, so you can review all this. Again, how are we setting up each of the cases. So I'm doing every single possible case, so you can see how it works. Okay, so